Here we formulated the objective function that minimizes the annual cost of ordering and storing. In this video, we will discuss separable programming problem in optimization. Here you can see optimization problem classified as integer and real value programming problems, deterministic and stochastic programming problems, separable and non-separable programming problems. Last one we have single and multi-objective programming problems. So optimization basic, its components like design variables, constraints, objective function, and different types of optimization problems: discrete, continuous, linear, non-linear, deterministic, stochastic, single, and multivariable. We already discussed in previous videos. Now we will discuss what is separable programming problem in optimization. So now we have separable programming problem. Suppose we have any function fx. Now this function fx is said to be separable if we can express this function as the sum of n single design variable functions. So here you can see we have a function fx is equal to sum of n single design variable function. Here you can see value we have up to, here you can see f1 x1, f2 x2, f3 x3, up to we have fn xn. So a separable programming problem is one in which the objective function and constraints are separable. So here you can see this is the standard form for the separable programming problem. Find x, which minimize this function and this function subject to different constraints. A function can be expressed as the sum of n single design variable, then we can say it is a separable programming problem. Second, if the objective function and constraints they are separable, then we can say the programming problem is a separable programming problem. Now we will try to understand separable programming problem in optimization using a numerical example. Here you can see we have a numerical example. So we have a retail store that stocks and sells 3 different models of TV sets. So this store stock and sells 3 different types of model of a TV set, and the store cannot afford to have an inventory worth more than $45,000 at any time. So this is the constraint, that the store cannot afford more than $45,000 at any time. Next, the TV sets are ordered in lots. So we will denote this cost with $AJ for the store whenever a lot of TV model J is ordered. Now the cost of one TV set for any model J is CJ. Now using CJ, we will denote the cost of one TV set for model J. We have 3 different models, so for each we will denote it. Next we have DJ, that denote the demand rate of TV model J, that is unit per year. Now the rate at which the inventory cost accumulate is known to be proportional to the investment in inventory at any time. So here we have a constant QJ, that is 0.5. That is the constant for the TV model J, and this value is remain constant, that is 0.5 for each model. We have 3 model value for J, we have 1, 2, 3. For each value for QJ remains same, that is 0.5. Now we have a store, it stock and sell 3 different type of TV sets. Now for the storage we need area. So each TV set occupy an area that is denoted with Sj is equal to 0.4 meter square, and the maximum storage space available in the store we have 90 meter square. So here in this problem we will minimize the average annual cost of ordering and storing. Now here you can see we have given a table, and in this table we have given data for the past experiment. Here we have AJ, that is ordering cost, CJ, that is unit cost, DJ, that is the demand rate. So value for J you can see we have 1, 2, 3. 1, 2, 3 represent 3 different models of TV sets. Then for each TV set, we have ordering cost, unit cost, and the demand cost. And here you can see all the values are given here. So suppose we have xj, that is the number of TV sets of model j. So with xj, we will denote the number of TV sets for any model j. Here value for j we have 1, 2, 3 because we have here 3 models. So here x1, x2, x3. Next we have the demand rate per year for any model. It is denoted with dj, and value for j again 1, 2, 3. d1, that is the demand rate for the first model. d2, demand rate per year for the second model. d3, that is the demand rate per year for model third. Now next we have total number of times any model is ordered. Now how we will calculate total number of times any TV model is ordered? It is dj divided by xj. dj, that is the demand rate, divided by xj, that is the number of TV sets of model j. So value for j again we have 1, 2, 3. So when value for j is 1, it means it is model 1. So it's demand rate divided by number of TV sets. Here d1 is the first model demand rate, d2 second model demand rate, d3 that is the third model demand rate, divided by total number of TV sets. Next you can see in the table we have given the demand rate for the first model, it is 800. For second model it is 400. For third model the demand rate is 1200. So here we can calculate this d1 divided by x1. For the first model demand rate we have 800, so it is 800 divided by x1. For the second model it is d2 divided by x2. For the second model demand rate we have 400, so it is 400 divided by x2. For the third model we have demand rate 1200, so it is d3 divided by x3. Value for d3 we have 1200, so it is 1200 divided by x3. Now next we have the cost of ordering any TV set. Now we will calculate the cost of ordering TV model per year. So it is calculated as aj into dj divided by xj. aj is here ordering cost into dj, that is the demand rate. Then we have xj, that is the number of TV set of the model. So here we have a1 d1 divided by x1. So a2 d2 divided by x2, a3 d3 divided by x3. Now you can see the data we have given. So here you can see in the table we have given the ordering cost for each model. For the first model it is 50, for the second one 80, for the third one it is 100. Then we have the demand rate 800, 400 and 1200. So now we calculate the cost of ordering for each model. For the first model, put the value here. A1 value we have 50, you can see here. Then the demand rate we have 800 and we got here 40,000 divided by x1. For the second model it is ordering cost we have 80, demand we have 400, so it is 32,000 divided by x2. Third we have ordering cost 100, demand rate we have 1200 and we got 1,20,000 divided by x3. Now we have the average level of inventory at any time during the year, that is cj into xj divided by 2. cj is here the unit cost and this is the number of model divided by 2. Here it is for the first model, it is c1 x1. Value for c1 you can see in the table. In the table you can see unit cost for first model 40, for the second model 120, for the third model it is 80. So here we will put the value for the first model, it is 40 in 40x1 divided by 2, that is 20x1. For the second model unit cost we have 120, we got 60x2. For the third model we have unit cost 80 and we got 40x3. Now we will calculate the storage cost. So the cost of storing TV set for each model, it is qj into cj into xj divided by 2. qj is here inventory cost, that is a constant value, we use 0.5. Next we have unit cost, that is cj. Then we have number of TV set, that is xj. For 3 model, it is q1, c1, x1 divided by 2 for the first model. For the second model, value for j is 2, q2, c2, x2 divided by 2. For the third model, j value is 3, q3, c3, x3 divided by 2. And all values are given in the table. You can see here cj value, aj value. We have given, put the values here. For the first model, we have given q1 value constant 0.5, it is given in the problem. Then we have c1 value 40, x1 as it is. Then we have 2, we got the value for this. So for the first model, we got the cost of storing TV set, it is 10x1. Next, we will calculate the cost of storing for the second model. It is constant value 0.5. Then we have c2, that is 120 x2 divided by 2, and we got 30 x2. For the third model, q3, again a constant. Then we have cost 80, then we have unit cost 80, and we got here 20 x3, that is the cost of storing the third model. Now you can see we have the objective function. You can see this objective function, it is the cost of ordering plus cost of storing that we already calculated before. So as we already discussed, suppose we have any objective function fx, and we can say this is a separable if it is the sum of n, if this is the sum of n single design variable function. Now we have n single design variable functions. Here you can see we have 3 single design variable function: cost of ordering plus cost of storing for the first model, cost of ordering plus cost of storing for the second model, cost of ordering and the cost of storing for the third model. Then you can see here x, it represents the design vector. Value for this we have 3 design variables x1, x2 and x3 that represent 3 models. Now we will discuss the constraints. So as you can see in this programming problem, we have first constraint that the store cannot afford worth more than $45,000 at any time. So this is the first constraint, it cannot worth more than $45,000 at any time. Second constraint, we have the area, that is the storage area that we need to store the TV models. So we have the first constraint, that is the constraint on the worth of inventory. So it cannot afford more than 45,000. So here you can see unit cost x1. Here you can see c1, c2, c3, that is the unit cost, x1, x2, x3, that is the first model, second model and third model. So all this, so this sum should be less than or equal to 45,000 because the store cannot afford more than $45,000. Next constraint we have for the storage, that is the limitation on the storage area, is denoted with sj. So value of j we have 1 to 3, so s1, s2, s3. Then we have model x1, x2 and x3, and the storage area we have 90 meter square, so it should be less than or equal to 90 only. Then the last constraint we have that the design variable values cannot be negative, so it should be xj. So j is here 1 to 3, so x1, x2, x3, it should be greater than or equal to 0. So now we substituted the values in the objective function. So here you can see in this objective function, it is the cost of ordering plus cost of storing. Here you can see cost of ordering we calculated for the first model 40,000 divided by x1. Cost of storing, you can see 10x1 we calculated. Like that we calculated for the second model and the third model. Now we have a objective function, and you can see this objective function is sum of n single design variable functions. Now second point we have, it's subject to different constraints. So here we have different constraints. You can see first constraint that it cannot worth more than $45,000. Then we have the storage constraint that we have only 90 meter square area and one model take 0.40 meter square. So for this we have second constraint. Then we have the constraint for the negative values. So now you can see this is a separable programming problem in optimization. We have an objective function that is separable, and it also subject to different constraints, and we have different separate constraints. So here we formulated the objective function that minimize the annual cost of ordering and storing 3 DB models, and it also subject to different constraints. So that's all about this video. If you have any question, you can comment below, and thanks for watching this video.